Okay, we're back from the break and we're still talking about performance estimates of simple devices. In this particular case, we're looking at the inverter, and we really just want to estimate sort of what kind of delay we might anticipate. So here's our simple schematic of our inverter and a load that it's talking to, which is basically the same gate or very similar gate, and then an input which transitions ideally. This over here is our equivalent circuit, and so you might ask yourself, so what is what on it? These guys here, the switch and the resistor, you might recognize as being the NMOS transistor, which is acting as a switch and it has some inherent resistance, and the PMOS transistor one acts as a switch with some inherent resistance. This is clearly the output node, and you might be able to recognize a capacitance contribution from the drain of the P-type device, a capacitance contribution from the drain of the N-type device, and then the actual other gate that you're talking to. So this would be the capacitance of the P-type transistor you're talking to downstream, and the capacitance of the N-type transistor you're talking to downstream, just as if you're talking to this other little inverter over here. So if you have this, you'd like to ask yourself, basically what is the delay? So this is a mini in-class assignment. We'll do it together and try to calculate what we expect our delay to be. Well, we can immediately sort of ignore a couple things here. These guys here where the capacitances are tied to a DC, we ignore them, and we're going to worry about the cases where we're going to take this output node and discharge it, or take this output node and charge it up. And so we're charging or discharging through R, and the capacitance associated with that circuit would be these guys all in parallel, so it's 2C plus 2C plus C plus C, so that's 6C. So we should be able to estimate that the delay through there would be 6RC, where R would be calculated from the IV characteristic of the transistor, and C would be estimated perhaps from parameters associated with the fabrication itself. And we'll talk a little bit more about that in the future. So here's a 3-input NAND gate with inverter type delay associated with it, or inverter type resistance, I should say. This is the simple schematic of it, just drawn with the transistors, the N and P type transistors. So you might recall these three here, the N type, they're in series, these three P type are in parallel. And what we want to do is we want to have associated with them different widths or different drive strength, and if it's a planar transistor, it's the width of the transistor. If it were a FinFET type transistor, it may be associated with the number of fins. So in this particular case, it's labeled as a 3 and a 3 here, and a 2 and a 2 and a 2 there. And a question might be, are these the W or L's associated with these devices? Well, they're clearly the W's. That's something you typically have more control over. The length is sort of set by the minimum feature that you're able to draw in that layer. So you might ask yourself, why is this now equivalent to an inverter with the similar resistance? So you could look at one of these. In the worst case scenario, one of the output node will be pulled up by one of these devices, and it has a width of 2. Okay, and if we look at the pull down part, we have 3 transistors here in series, so it looks like it's going to have an overall aspect ratio of 1. So you might say that the pull down section looks like it has an overall W over L ratio of 1, the pull up section a W over L ratio of 2. Taking account for the fact that the mobility of the electrons is greater than that of holes, we're going to get roughly equal resistance in the pull down and pull up sections, and equivalent to the minimum size dimension transistor you can make for an inverter. It gets a little bit more complicated here, and basically what we've done is just added all the capacitances that are associated with those layers. Some of them perhaps a little more clear to figure out than others, and some perhaps a little less so. So in this particular case, for example, the gate of this NMOS transistor has associated with it a 3C because it's of width 3. The gate of this, let's go over here, the gate of this transistor here, which is P-type, it's of width 2, so it has a capacitance associated 2C be associated with it. And these other capacitances here are similar to what we saw for the inverter. This would be the drain capacitance of this NMOS transistor, so you would attribute it to be 3C. So basically what we've done here is instead of having one circuit talk to an identical circuit, we just move the C's from the output to the input, and that's just a matter of convenience. The capacitances on the source diffusions are connected to ground or VDD. are shorted out. So that what that basically means is these guys down here and these guys up here, we don't have to worry about. They're typically out of the picture because we're not putting any charge on them or taking any charge off of them, so they won't contribute to the capacitance of the associated with the delay. The DC terminals effectively are irrelevant, as I sort of said, and as such, we sort of consider C as having a bottom plate tied to ground. So even if this were the case up here where these are tied to VDD, we still think of them as being tied to ground. And then at that point in time, when we're trying to make some kind of estimate what the performance is, we combine parallel and series capacitors or resistors as we usually do. And most importantly, at this point in time, you cross your fingers. So we're going to approximate the 3-input NAND C's and R's, and we're going to get a delay estimation, and it's called an Elmore delay. And this is sort of an equation for it. Actually, it's not a very accurate equation because it only looks at capacitances. This is slightly more realistic, where you worry about the capacitors that you're charging and discharging and the resistance at which you're discharging and charging them through. So here's an in-class assignment 5.6. What is the worst case pull down for the 3-input NAND? So in that particular case, you're going to worry about taking this output node here and pulling it down through these NMOS transistors that are in series. And I've sort of summed up some capacitances here on the gates to make things a little simpler. And I summed up the capacitances seen on the diffusion here by this transistor associated with the diffusion of each of these transistors as well as this NMOS transistor. So that's for you to do, and I'll sort of show you how you might go about doing this and answer the question, what is the worst case pull up for the 3-input NAND gate? So in that particular case, we're going to worry about worst case, so that means we're pulling this output node up through one transistor in the pull-up section. And here's a guess that I came up with, and I'll go through it in a bit of detail in a minute. Basically 2/3 plus 1 R3C plus 1/3 plus 1 R3C plus 14 R14C, for a total of 23 RC. And breaking it into little pieces here, this is where the first one comes from. I have this 3 C capacitor here, and I'm charging it up through an NMOS transistor of width 3, an NMOS transistor of width 3, and a PMOS transistor of width 2. So this is an equivalent resistance of R, and this is equivalent resistance of 2/3 R, because we have a length of 2 here and a width of 3 as an overall aspect ratio. We do that for the next 3C capacitor here. We're going to charge it up through this one NMOS transistor and this one PMOS transistor. So this has a resistance of 1 R, and this is a resistance of 1/3 R, because it's of width 3 and of length 1. So we get that middle term, and then we worry about the last term, and that's where we're going to charge up the output node, which is 9C plus 5C, so that's 14C through 1 R. And that combines to give us 23 RC. So the assignment number 3, I guess. So it says assignment October 2, due October 3. I'll have to fix that. Anyway, it's just more fun with R and C. It's the assignment I just gave you, and we'll also do the same thing with the NOR gate. So you start here by filling in the blanks that are identified here with aspect ratio of those transistors, such that it overall has a inverter R-type characteristic. So the pull up and pull down worst case will resemble R for the resistance of those devices, either in series or in parallel. Again, we go through the same process here. We take the output capacitances and move them to the inputs for convenience, so we don't have to draw the figure over again. The caps on source diffusions connected to ground or VDD are considered shorted out. They're not in the picture anymore. The DC terminals are irrelevant, so we basically think of the bottom plate of the capacitors as all being tied to ground. Then it's relatively straightforward to combine parallel and series capacitors or resistors as we usually would, and again, cross your fingers. So the questions then for this part would be, what is the worst case pull down for the 3-input NOR, and what is the worst case pull up for the 3-input NOR? Sort of ignoring that equation, but you can basically use that one here in a very similar manner to how I illustrated it in a couple of slides back. Some rules of thumb values, keep in mind. This isn't exactly how it is, but it's not too unreasonable. Capacitance, you can sort of think of it as having a capacitance associated with the gate, the source, and the diffusion. Those are the major causes of capacitance. And they're on the order of 2 femtofarads per micrometer of gate width. And these values appear to be quite similar across many processes. And resistance here's an example of a process which R was 6 kilo ohms times the number of micrometers, and that would be the length, let's say, of a transistor in a 0.6 micron process. And if you have a fan out of H, you just multiply the next gate input capacitance by H. The important point here is that's femtofarads and kilo ohms, and that's why devices operate at the speeds they do. And at this point in time, we'll take a brief break.